Hey guys, we're on Unit 5, and this is day 2, and we are going to talk about proving triangles congruent using what I like to call a shortcut theorem. But before we get there, let's try warm up, and it's talking about given ABC is parallel to DE. Okay, one way to mark parallel lines is by putting those little arrows on there, if that's helpful. Okay. The other thing about parallel lines is it's also helpful to trace over a transversal that cuts through or meets both parallel lines. And we have two options. In this one, we have BD as our transversal, or we have BE as our transversal. So not quite sure which one we want to use first. But if I'm trying to think about how to make this problem a little bit easier for you, we're going to use BE as our transversal. Okay. All right. The other thing that we have to notice, guys, is that we have a bunch of triangles. And some of those triangles, like this one, already have two angles in there. So we can go ahead and find the third angle using our triangle sum of 180. So we'll go ahead and say 180 degrees. Take away the 130-degree angle. Take away the 25-degree angle. Is going to leave us with 25 degrees for the remaining angle, which will go right here. Okay. I don't know if you noticed this yet, but this angle right here is going to be the same as this angle right here. Those are called alternate interior angles, and alternate interior angles are congruent, so I can bring the 25 up here. Okay. All right, so we used our parallel lines. We used a couple of the numbers that they gave us, and now we have to recognize that the angle that we're solving for, if you notice right here, guys, is lying on the same line as the two other angles next to it. So this angle of X, that 90-degree angle, and the 25 that I just put there, those three angles have to add up to equal 180 degrees because there's three angles next to each other on that line. Okay, so if I take 180 degrees, I take away the 90-degree angle, I take away the 25-degree angle, I will be left with my answer for X, which is 65 degrees. Okay. The other way you could have done this question, just to show you guys that you have a linear pair right here with the 130, and so this angle here is 50. You also have a triangle with two angles you now know, 50 and 90, and so this angle is 40. And right here, this angle of 65 degrees, 40 and 25 together, is the same as this angle here, and so this is 65, which is the same answer that we got. It's just that this is a different transversal that we can use with that alternate interior angles on here. Okay. All right, guys, so we are going to prove triangles congruent. So when we talked about congruent triangles before, we said that if all 6 parts of one triangle have the same measures as the corresponding 6 parts of another triangle, then the two triangles can be said that they're congruent. Or if there's a rigid motion that maps the one onto the other, then we could say that they're congruent, okay? But a long time ago, a mathematician came along and said, you know what? I've tested this theorem and it works. And his theorem says if you have these specific 3 parts, 2 sides, and the angle in between the 2 sides, then these 2 triangles I have proven have to be identical twins of each other if only those 3 parts match. And so you don't have to get 6 parts anymore. If you go and use my theorem called side angle side, where the A or the angle is between the 2 S's or the 2 sides, my theorem will work. All right. And so you'll see markings in the pictures to show that theorem. So his theorem again says if 2 sides and the included angle of one triangle are congruent to sides and the included angle of the other triangle, then the 2 triangles are congruent. They are identical twins, okay? So in these pictures here, they have one side tick mark, meaning that that side is congruent to that side. They have a second side double tick marked, meaning that those 2 sides are equal. Okay? And notice right in between those 2 sides is the angle. And that angle has that arc mark in it. Okay, and it has to be that angle to be between those 2 sides. Just like in his theorem, he named it specifically SAS. Okay, that angle has to be between the sides in his theorem, and it has to be between the sides in his picture in order for his theorem to work. Okay, and so we're going to go through a bunch of pictures and see if this is a good indication of his theorem or not. So in 1 through 4, it says the given information, is the given information sufficient to prove congruent triangles using side, angle, side? So if we look at the first one, guys, notice that there are 2 sides marked. Okay, and in the second triangle, we have 2 sides marked. Okay, and in the back to the first triangle, this right angle, guys, is the same 90-degree right angle here. So it's not an arc mark, but it's even better because it's giving a number where I can know 100% that that angle is identical. And so that is the angle in between those 2 sides. Okay, and it's the same here, that angle is between those 2 sides. And so this is a yes. These 2 triangles are congruent. We can say triangle LAP is congruent to triangle ORP by side, angle, side. Okay. All right, guys, number 2. And so in number 2, you're going to notice something, guys, and I'm going to use my highlighter since the triangles are touching each other. But this is one of my triangles. And notice, guys, that there's only 2 pieces marked, one side and one angle. Okay. However, you are going to see that it's kind of what I call back to back with my other triangle. And because it's back to back, they're sharing a side. And that side, guys, that gets shared is called a reflexive side. All right. And we mark it usually with an X, X for reflexive. All right. And that's actually a second side in that red triangle. Okay. If I look at my blue triangle here, right now it has a side that was tick marked, the angle, and then the reflexive side, because it's shared, counts in both. All right. So back to my red triangle, I have a side here and this reflexive side here. Okay. Notice that the angle I have is in between those 2 sides. Okay, let's check the blue triangle. In the blue triangle, guys, I have the reflexive side again and the single tick mark side. The angle that has the arc mark in it, okay, that's an angle, and it's between my 2 sides. And so this is a yes. Okay, we can go ahead and say that yes. Okay, these triangles don't have names, so we could just say triangles are congruent by side, angle, side. Okay. Let's take a look at number 3. Again, guys, these triangles are kind of stuck to each other, so sometimes it helps to highlight them and see. But in that red triangle, guys, you do have 2 sides marked. In the blue triangle, you do have 2 sides marked, so we'll use the sides that they have. Oops. Yeah. And right here, guys, that angle that's marked is in between your 2 sides. Okay. Here, guys, the angle that's marked is in between your 2 sides. And so this is, again, a yes. They didn't name the triangle, so we'll just say yes. Triangles are congruent by side, angle, side. That's the theorem that the mathematician came up with that proves those 2 triangles are identical twins. Okay. And in the last one, those triangles, guys, are not stuck together, so you don't have to highlight them. I think you're okay with them being separate like that. But take a look, guys. They do have 2 sides, each marked. Okay. And each one has an angle. However, guys, that side is sandwiching that angle on that side, but this side, guys, isn't marked to sandwich that angle on the other side. And so this is not side, angle, side, because the A is not between the 2 S's. In order for the A to be between the 2 S's, guys, it would have had to been this angle up here that I'm shading in red. Okay, that's the angle that would have been between those 2 sides that are marked. And because it's not, this is a no. All right. In fact, that theorem, guys, is actually called, and it's not a theorem, so I shouldn't even call it that, but that would be a representation, guys, of what I call ASS, where the A is not between the 2 S's. And so hopefully you realize that, although a bad word, okay, is not going to be a theorem that is used in geometry, okay? So maybe you can remember that we should not have any donkey theorems in geometry to prove triangles congruent because that will not prove congruence. In fact, we have 4 left to learn, and that's never, ever, ever going to be one of them. All right, so no donkey theorems. Okay, if you get my drift, no backwards donkey theorems either. And a backwards donkey theorem would be spelling the donkey backwards. That also, guys, is not going to work. Okay, so we are going to go ahead and say no, triangles are not congruent. Those markings do not prove that those two triangles are going to be identical, even though it looks like they are. Right now, we only have one theorem, and that doesn't pass that theorem test. Okay, and so hopefully that helps. And then we're going to go through another theorem on day 4. Okay, I will see you guys there.